Welcome back. We're going to continue our discussion and start to talk about capacitors and capacitance. So capacitor is a device that's used to store electrical charge. Okay? And the amount of charge a capacitor can store depends on voltage applied and its physical characteristics like size. Okay? An example of a capacitor would be a battery. A battery is very much used, used a lot, and so we see this all the time. Okay, this is very common, but we just don't know the physics behind it. So a capacitor can hold some amount of charge, and we call that amount of charge that is stored per volt the capacitance. Okay, so we call this C. Okay, that's how it is represented. And capacitance is equal to our charge divided by voltage. Okay, and capacitance is measured in farads, I believe it's called. Farads. I could be wrong, but I believe that's how you spell it and pronounce it. And that is equal to 1 coulomb over 1 volt. Okay, and this is an example of one. Again, this kind of looks like a battery, but we have a parallel plate capacitor here. And let's talk about that a little bit. This is a parallel plate capacitor. We have two plates that are parallel, you guessed it. And on one of the plates, it has a charge of positive charges, and on the other plate, we have negative charges. Okay, these plates have some area A and have some separation D between them. Okay, and this is hooked up to a battery with some voltage. Okay, so the capacitance of a parallel plate capacitor is equal to epsilon naught, which is a constant. This is a constant. Times the area of that plate. So let me say area of the plate divided by that separation distance. Okay. And note that we have these units here, farads over meters. That's the same as Coulomb squared divided by Newton times meter squared. Okay, so these are just some notes on the units. But yeah, this is how we calculate the capacitance of a parallel plate capacitor. Okay, so let's go ahead and do that. What is the capacitance of a parallel plate capacitor with metal plates, each of area 1 meter squared, separated by a distance of 1 millimeter? Okay, so this is our area A. This is our separation distance D. Okay, so C is equal to epsilon naught times A over D. Okay, A is good. Let's go ahead and convert this into meters. So this, remember that millimeters to meters is times 10 to the negative third. So this is just 10 to the negative third meters. Okay, so let's go ahead and calculate this. Epsilon naught is 8.85 times 10 to the negative 12th. So 8.85 times 10 to the negative 12th farads per meter. Right? Double checking. Perfect. Times our area, which is 1 meter squared, divided by our separation distance, and that's 10 to the negative third meters. Okay. So we'll just need to put that into our calculators. So 8.85 times 10 to the negative 12th times 1, right, divided by 10 to the negative third. Right, so we get 8.85 times 10 to the negative, ninth, and our meters will cross out one here and then cross out the other here, so we are left with farads, which is perfect. So this is our capacitance of that parallel plate capacitor. Okay. Now the second part asks what charge is stored in this capacitor if a voltage of 3.00 times 10 to the third volts is applied. So we want to know Q, charge stored. Okay, so let's go back a couple to find that formula again. So our capacitance again is equal to Q over V. So C is equal to Q over V. So we now have our capacitance, we found that, and we have our voltage that was given. So let's find Q. It's going to equal V times C. Okay. Our voltage is 3.00 times 10 to the third volts. C is 8.85 times 10 to the negative ninth farads. Okay. So we'll put that into our calculator. And we get a charge of 2.66 times 10 to the negative fifth, and charge is in coulombs. Okay. If all of the letters confuse you, you can always do it a little differently on your own work. So you can say this is coulombs. Okay, just make note of it. This is capacitance. Okay, don't confuse yourself. Take your time with this, okay? All right, let's move on to the energy stored, not stores, stored in capacitors, okay? It can be expressed a few different ways, and not going to go through the big details about this, but the energy stored in capacitors, or E sub CAP, is equal to Q times V over 2, where Q, of course, is the charge, V is the voltage. You can also rearrange that for C times V squared over 2, where C is the capacitance and V again is the voltage. Or you can rearrange it again to be Q squared, or the charge squared, divided by 2 times the capacitance. Okay. So again, note the units here. I have them noted. Energy is in joules, of course. Charge is in coulombs. Voltage is in volts. And capacitance is in farads. Okay, what did I write before? Maybe I wrote faradads? Yeah, I did. I just went too far there. Farads. Okay. All right, sorry, my dog is going crazy right now. All right, so with that information, let's go ahead and have one more example. It states a heart defibrillator delivers 4.0 times 10 to the second joules of energy. So this is energy. By discharging a capacitor initially at 1.0 times 10 to the fourth volts. So that, of course, is our voltage. What is its capacitance? C. Okay, so let's go back. Actually, let's think. We have E, V, and C. E, V, and C. So this here, this is what we want to use. So E capacitance is going to equal C V squared over 2. solve for C, and we get 2 times the energy divided by V squared. So we can plug everything in here. V is 1.0 times 10 to the 4th volts, and that is squared. Okay, so we can do that in our calculator. Divided by 10 to the 4th squared. Yeah, so that gives us 8.0 times 10 to the negative 6th. And this capacitance is in farads. Okay. All right. So I believe that is all. So again, if you guys have questions, please ask me. And next time we're going to look at electric current, resistance, and Ohm's law. With that, we are also going to be looking at the capacitors in series and parallel that we didn't talk about this time. That is section 19.6. So we're going to kind of lump sum that in just because we talk about what it means for a circuit to be in series and in parallel. So I kind of want to talk about all of this stuff together at the same time. Yeah, and I think that's all. So again, I'm going to remind you for like a 17th time, please let me know if you have questions. We will have time in class to go over this. So yeah, we will talk soon.